Today we want to look at how you can represent a function using a table, using a graph, using an equation. A function rule is an equation that describes the relationship between inputs. Inputs are your independent variables. All right, inputs are also your domain values, and your outputs, which are your dependent variables or which are your range values. Okay. If you have the function rule of y is equal to 3 times the number x and your input is 2, 3 times negative 2, your output's going to be negative 6. So if you're asked to write a function rule or a rule for a function, you're just being asked to write an equation that represents that function. Okay? All right, let's take a look at problem number 1. Write a function rule for the output is 5 less than the input. Well, your output is always your y values. Your output is always an equal sign. Your output is 5 less than. We have to subtract 5 from whatever the input is, and that would be x. So y is equal to x minus 5 is the function rule for the output is 5 less than the input. All right. Write a function rule for the output is the square of the input. Your output is your y. This is your equal sign. The square of the input. Well, your input is x, and we are squaring that input. All right. Next. What is the value of y is equal to 2x plus 5 when x is going to be equal to 3? Well, we are all familiar with this type of function. Our output is y, our input is x. So we take the rule and we place our input with 3. So y is going to be equal to 2 times 3 plus 5. Y is equal to 2 times 3, which is 6, plus 5. So y is equal to 11. So your output is equal to 11 when your input for this function is 3. All right, we'll do each one of these down here. We are asked to find the value of y when x is equal to 5. All right. Oh, well, let's do number 1. Write a function rule for the output. Y is 1/4 of the input, right? So that would be your rule for number 1. Okay, number 2. We want to find the output when the input is 5 for each function. So y is going to be equal to 4 times 5 minus 1. Y is equal to 4 times 5, which is 20, minus 1. Y is going to be equal to 19. Second example, y is going to be equal to 10 times our input of 5. Y is going to be equal to 10 times 5, which is 50. Normally, when you replace a variable with a number, you want to remember to use parentheses to show that. All right, our output of y is equal to 7 minus 3 times our input, and our input's going to be 5. Y is going to be equal to 7 minus 3 times 5, which is 15. 7 minus 15. Y is going to be equal to negative 8. All right, next page. Functions as tables and graphs. A function can be represented by an input-output table and by a graph. The table and graph below represent the function y is equal to a number x plus 2. If we look at our inputs and outputs here, each one of our outputs is 2 more than our inputs because our function rule is the output is equal to the input plus 2. So 4 is 2 plus 2. 5 is 3 plus 2. Well, we represent that relationship with our ordered pair. So we pair together our input of 1, our output of 3, and we create our ordered pair 1, 3. If our input is 2 and our output is 4, our ordered pair would be 2, 4. If our input is 3 and our output is 5, our ordered pair for that function would be 3, 5. Graphically, we know that we can take our ordered pairs that we just created and graph them on a coordinate plane. So 1, 3 is located here. We have 2 and 4 is located here. 3 and 5 is located here. And we can see that it's a linear function because the points fall in a straight path. All right, and by drawing a line through the points, you graph all of the solutions of the function y is equal to x plus 2. And we see it is a continuous function because we can replace x with anything. I could replace x with 1/2. I could replace x with 1/3. I could replace x with, negative 2 billion. All right, and I can always add 2, so that's a continuous function. All right, we continue. Graph the function y is equal to negative 2 times x plus 1 using inputs of negative 1, 0, 1, and 2. So our inputs are going to be negative 1, 0, 1, and 2. In our table, this is going to be negative 2 times negative 1 plus 1, negative 2 times 0 plus 1, negative 2 times 1 plus 1, and negative 2 times 2 plus 1. We evaluate the function for the output. Negative times negative is positive, so that's positive 2. Positive 2 plus 1, the output's going to be 3. That's 0. 0 plus 1, our output's 1. This is negative 2 times 1 is negative 2. Negative 2 plus 1 is negative 1. Negative 2 times 2 is negative 4. Negative 4 plus 1 is going to be negative 3. We take our input, we take our output, we pair them together to create our ordered pair. So our first ordered pair is negative 1, comma 3. Our second ordered pair is 0, comma 1. Our third ordered pair is 1 and negative 1. And our fourth ordered pair is 2, comma negative 3. All right, we can put those ordered pairs on a coordinate plane. So let's do that, right, by graphing the ordered pairs. Negative 1, comma 3 is going to be located here. 0 and 1 is going to be located here. 1 and negative 1. It's located there. And then 2 and negative 3 is going to be located here. We have a collection of points in a straight path. Right, we want to show all of the solutions for the function. So we extend that as far as we can. Let's put arrows at the end of our line, right, to show those solutions go on forever. All right, our next problem. Right, we want to graph each of these functions. So our next function is y is equal to x plus 1. All right, instead of making a table, which I know we can do to show the input and output relationship, we can graph these functions, the way we normally do, because each of these functions are in slope-intercept form. So we'll just do that, and we can do that because we know that our line shows all of the solutions to that function. So we'd start at positive 1 here, and our slope tells us to go up 1 over 1, up 1 over 1, up 1 over 1. All right, we get a collection of points in a straight path. All right, let's draw that neatly. Extend our line and arrow. So that's our y is equal to x plus 1. Our second one, y-intercept is 0, and then the slope is down 3 over 1, down 3 over 1, down 3 over 1. Get a collection of points in a straight path. All right, we'll graph that line. Should look something like that. All right, I'm just going to make that purple to match our, right, I'd like to make it purple. Oh, here we go, purple. Make a nice purple. There we go. And let's draw arrows at the end of that line. All right, there we go. And then our last one, y-intercept is 2. We point at 2. Then from 2 we go up 3 over 1, up 3 over 1, up 3 over 1, get a collection of points in a straight path. All right, we'll draw that line, and that should be good. Draw arrows at the end of that line, arrow, arrow. All right, nicely done. We continue. Here it says the number of pounds, P, of carbon dioxide produced by a car is 20 times the number of gallons, G, of gasoline used by the car. Write and graph a function that describes the relationship between G and P. Here's our function rule. P is going to be equal to 20 times G. Right? We put that in the form of a table. Right? We're going to evaluate this function for inputs of 1, 2, and 3. So that's going to be 20 times 1, 20 times 2, 20 times 3. Outputs are going to be 20, 40, and 60. Our ordered pairs, 1 comma 20, 2 comma 40, and 3 comma 60 for our ordered pairs. Good job. Next, we talk about linear functions being discrete and continuous. We've talked about this earlier, but I just included the slide for the lesson. All right, but let's see. Well, a linear function is a function in which the graph of the solutions form a straight line. Therefore, an equation of the form y is equal to mx plus b, that's a linear function. A function can be considered continuous or discrete. Continuous data can take on any value, so there is no space between data values for a given domain. Discrete data have space between possible data values. Graphs of continuous data are represented by solid lines, and graphs of discrete data are represented by dots or points. Continuous data, some examples would be the number of ounces in a glass or the weight of each chocolate chip. Continuous data I like to identify as something you can count. All right, so continuous data you can count. Or, my bad, I just did that backwards. You know, continuous data is a measurement, right? That's your measurement, the continuous data, right? Measurement is your continuous data. And then we have our discrete data, the number of glasses in a cupboard, the number of chocolate chips in a bag. That's your count. Something that you can count would be an example of discrete data. All right? If the domain of a function are integers, this is an example of discrete data. If the domain is all real numbers, right, meaning fractions, decimals, you know, anything in between 0 and 1 or anything between any two integers, this is an example of a continuous function. All right? A store sells assorted nuts for $5.95 a pound. Write a function to represent the total cost for any number of pounds of nuts. Complete the function table below to find the total cost of 1, 2, 3, 4, or 5 pounds of nuts. Graph the function. Is the function continuous or discrete? And explain. All right, so we're going to have, let's see, input, output, and this is going to be 5.95 times the input. Our input value is going to be 1, 2, 3, 4, and 5. So this is going to be 5.95 times 1, 5.95 times 2, 5.95 times 3, 5.95 times 4, and 5.95 times 5. The output, what's that? 6 times 1, take away 5, so that's going to be 595 for our first input. This is 6 times 2 is 12, so that's going to be 1190. 6 times 3 is 18, so that's going to be 1785. 6 times 4 is 24, so that's 2380. And then 6 times 5 is 30, so that's going to be 2975. If we're labeling our axes across the horizontal axis, that's going to be, let's see, pounds of nuts, right? Pounds, right, of nuts. This will be the cost of the nuts along the vertical axis. 1 pound of nuts, our input and output, is $5.95. It's going to be a little bit above 5. 2 pounds of nuts is $11.90. That's going to be, I guess, a little bit less than halfway up. 3 pounds of nuts is going to be $17.85. 3 and $17.85. It's going to be about here. And try to cheat and put your data in a straight line because it should be linear. 4 pounds of nuts is $23.80. Here's 4. $23.80 is going to be a little bit less than 25. And then 5 comma 29.75. It's going to go right here. Put the points, connect the points with a straight line. arrow at the end. And that's what the graph of that linear function would look like. All right. I think we'll take a look at these last couple of questions here. Each person that enters a store receives a coupon for $5 off his or her entire purchase. Write a function rule to represent the total value of the coupons given out. Let y represent the total value of coupons and x represent the number of people. The function rule is y is equal to 5 times x. Make a function table to find the total value of the coupons given out at 5, 10, 15, and 20 customers. Here's your input-output table. All right. And this would be an example of, because we can count customers, we can't have partial customers, right? This would be an example of discrete data. And discrete data is something that we can count. We can count the number of customers. That's our along our horizontal axis. Right? And that would be an example of discrete data. All right, we're going to stop the lesson there. I hope that's been helpful, and we'll see you soon.